All right, so number 13, it was the last one, right? That means that's the one you skip or you just copy from the key because you're tired, right? That's what that means. No, it says calculator permitted, all right? The Beer Lambert Law has nothing to do with alcohol, all right? The Beer Lambert Law has to do with how light is absorbed in water, right? Has anyone ever been to the bottom of the ocean? Right? Not only is it very pressurized down there because water is heavy, but it's kind of dark, right? It's kind of dark at the bottom of the ocean. But at the surface of the ocean, it could also be pitch black dark, right? If you're there at night. But during the daytime, it's lit up. And as you dive down into the water, it gets darker and darker and darker because water does absorb light. And it absorbs light according to this log function called the Beer Lambert Law. All right. Now, in science class, you probably call this a formula, right? A formula is something like on a chart that you pull out. It has some unknowns. You plug them in, you evaluate it. But a formula is nothing more than what's called a literal equation. Literally means by the letter. So if you see an equation that has multiple letters in it, you can call it a formula, you can call it an equation, but it's a literal equation, all right? Now notice it's not solved for any particular variable, but when we have a mathematical model and we apply it to real life situation, I mean, that's the purpose of math, right? To make sense of the world. We typically change the variables, so it's no longer just boring X and boring Y, right? We use those variables to help us study. We usually change them into something more meaningful, like time for our independent variable. But in this case, we kept X, and if you read, X is the depth in feet, and then I is the intensity of the light, which a lot of people have experience with because people purchase headlamps and flashlights, right? And they're always advertised like 50,000 lumens, right? You can disturb your neighbor at night with this flashlight. Okay, so there's two questions here. It says, what is the intensity? So we're looking for I of the light at a depth of 30 feet. So that's when X is 30, right? So when X is 30, what is I? Now, again, notice this equation is not solved for I, nor is it solved for X. So we have two options here, okay? We can either A, solve it for I and leave X in there. And then after we solve it for I, we'll call this A, we can solve it for I equals, but when we do that, it'll be a function of X, right? That's why we use function notation. You'll have an I on the left side, and you have all the numbers and operations and an X on the right-hand side. So we can solve it, and then we can plug in, right? I of 30. That's how we communicate mathematically with functions that we're going from a variable equation to a numeric equation, right? I of X versus I of 30. Now, we could also plug in and then solve, okay? This would be solve, then plug in, versus part B or option B. We'll call this the first part I. Part B, we can plug in, then solve. Now, I asked you, first of all, is there any benefit in any situation to one of these versus the other? Yes, very much so. When would it be advantageous for us to solve for I in terms of X and then plug in an X? When would that be better? For the calculator? Well, yeah, it says calculator permitted. The calculator is going to do nothing unless we tell it to, right? So as I told you, when it's a calculator question, you always do your thinking first. You always write down on your paper or iPad first what it is you're going to plug into the calculator. So whether I solve for I and then plug in and then type the right side into the calculator, or I plug in and then solve manually and then plug into the calculator, it should be the same thing when I plug it into the calculator. But look at this option. What if I wanted to figure out the intensity, not just at 30 feet, but I wanted to figure out the intensity at 10 feet, 20 feet, 30 feet, 40 feet, 50 feet, like a whole bunch of different depths? Would it be better to solve once and then plug and chug? Or would it be better to plug in each of those different depths and solve it with all the algebra each time? See what I'm saying? If I solve for I first with all the variables intact, Then if I want to figure it out for different depths, x, I can just plug into the right side. I don't have to do the math anymore. It's literally plug and chug, like finding a y-intercept on a graph. If I chose to plug in and then solve, think about it. I would have to plug in different values of x into this equation. And then every single time I would have to solve for I. I would have to redo all the math each and every time, right? So that's why we want to do part A. If we have, this would be advantageous if we had for multiple x values, right? But if we're only interested in one depth, then we might as well just plug in and solve. This would be for one calculation only. Now, the reason we might want to do that, because we can still do the other version, right? If I wanted one calculation, I can still solve for I and plug it in, no big deal. But here's the deal. It is a lot easier for y'all to manipulate numbers in an equation than it is to manipulate variables, because you raised on numbers. Variables came next, right? There's this running joke about if you go to hell, you're going to eventually run into the guy who introduced the alphabet into math, right? That's yeah. So let's do that. Since we're only looking at for one calculation, let's go ahead and plug in and then solve. Now, here's the next point that I want to bring up. I always have to communicate what I'm doing, right? That's the goal of this class, to clearly communicate. So when it's in function form, and I'm going to be plugging in a 30 for x, it's easy to show that, right? I of x becomes I of 30, boom. But how do we communicate that we're plugging in a 30 for x when it's not solved for I like that? We can't do I of x. Well, guess what? We can still do. We could still do this. Not in a highlighter. When x equals 30 colon, right? Remember when we found the inverses, I put the $sign and I put $sign colon? Just like when we did domain, big D, I put D colon instead of D equals. These are your stage notes. These are your mathematical stage notes. You're annotating your problem, essentially. You're communicating to someone what you're doing. When x equals 30 colon, oh, I know what they're doing now. They're plugging in a 30 for x, okay? That's how you do it. Now, you could still do it up here. You could say when x equals 30 colon, and then do I of 30, but you don't need to, okay? This is optional here because you have I of 30. All right, so let's practice that. When x equals 30, now we plug it in. We're going to get log of I over 12 equals negative 0.00, two zeros after the decimal, 235, and then parentheses 30. When you're plugging in a number, especially if one of them's negative, try to use parentheses, because you should never put dot negative. If you put dot negative, that's times the negative number, I'm going to growl like Papa Bear did when he found Goldilocks sleeping in their bed. Grrr. Don't do it. All right. So now I'm going to solve for I. Okay. Now notice I have a number on the right-hand side. I'm not picking up my calculator yet. Why? Because then I'm just going to store a bigger number. Just leave it like that. To peel back the layers now, I have to unlog it. By the way, what's the base if it's not written? 10. Okay, good. How do I unlog base 10 something? We can either go around the world or exponentiate base 10. Either way, right? If you exponentiate base 10, remember I told you could do this. You can get away with putting a little 10 to the bottom left, which makes each side now exponents. You eventually want to get away from doing that because you don't need to show that. All right. But in temporary, you can. Now, you could also do the around the world. Okay, that works as well. 10 to the other side equals I. Again, you could draw the arrows if you want, but eventually get away from it. What we really want to see is just the next line. Mathematics, we don't really need to show that. We just go to the next line. So we have 10 to the negative 0.00235 times 30th. equals I over 12, right? And now it's easy. How do we undo dividing by 12? We multiply both sides by 12. And again, you could show times 12 times 12, right? There's nothing wrong with that, but it's unneeded. Hopefully you know what you're doing. That's just kind of a temporary thing when you're learning how to do it. As long as the equation is still the same, you're okay, but it doesn't really show your process. So I'm just not going to show that. And I know that I'm going to get 12 times dot 10 to the negative 0.00235 times 30th, or to the 30th. And I know that that's going to equal I. So now I'm going to put that I on the left-hand side. I solve for I one time. Okay, now I'm going to go to my calculator. Go to the calculator. Now, finally, and I'm just going to type that in. 12 times 10 caret. And then I go negative 0.00235 times 30. Click to the right. Did I do that? 12 times 10. And your calculator is going to do it in the right order, right? It's going to do the exponent first, and then the exponent it's going to multiply. Then it's going to do 10 to that power, and then it's going to take that number and multiply by 12. Okay, hit enter, and there it is. We get I equals 10.201 or 202 if you round. I don't care, 3 decimals. And now here's the other thing that I want to do this problem for, to point this out. On your final numeric answer in a problem where there's units, on your final numeric answer, you better put what? Units, right? What are the units of I intensity? Lumens, right? Lumens. So according to this Beer Lambert law, you know, at 30 feet deep, the intensity has diminished. 12, if you look at the denominator 12, that's called your basis, all right? That's kind of the standard bearer. So you're comparing it to the original. So essentially you've lost almost 2 lumens at 30 feet. Now, another quick word. We like to learn in here, right? A.A. Milne wrote which series? A.A. Milne? Winnie the Pooh, good. And this picture of Jacob Redding is from this year or last year? It's from last year. Okay, good. If you write an I versus an I like this, sometimes the capital I, like the top one, is okay. Context clues, but sometimes it's not okay, right? Because sometimes it can get confused with what? The number 1 or the lowercase letter L, right? So in this case, we write it with the horizontal division bars. Well, that's not the horizontal division bar. We write it with horizontal bars. These actually have a name, like the horizontal division bar is called the, I always forget, the obelisk or whatever. These are called serifs, okay? So this would be with serifs, and you've probably seen this on like Microsoft Word when you're looking for different fonts. Have serifs fonts, and then this would be without serifs, or in Latin, we call it sans. Sans means without, okay? So we're learning new things in here. Serifs are the little tails you give on your numbers, right? Sans means without. Back in the day, there was a real popular line of gentlemen's trousers for middle-aged gentlemen called Sansa belts, right? As men get older, their waistline kind of gets a little bit bigger and then smaller. And so, you know, I have belt loops here, but I didn't wear a belt today because, you know, they're tight enough that they won't fall down because my belly is middle-aged belly. Although I've lost 10 pounds since New Year's Day. So thank you very much. No need to clap. But back in the day, my father wore these pants called Sansa belts. You can look them up, Sansa belts. And they were adjustable. They didn't have elastic. They did have a little elastic in them on the front, but you just clip them, and you can clip them at different tightnesses, right? So, you know, if you have a big meal, you know, like, ooh, that was some Taco Bell, loosen it up, right? People that wore Sansa belts usually didn't go to Taco Bell. Anyway, they were very popular, very popular. Sansa belts, perfect name for trousers, slacks that had no belts, right? You can probably still find them today in my dad's closet or at thrift stores, right? Jacob, did you look up Sansa belts? Yeah, they're a real thing, right? Yeah. Sansa belts. Pretty nice. Let's bring back Sansa belts. No belts, right? So anyway, serifs, no serifs. All right. Now, if we're going to do it for the other version, right? Let's do it for the other version. Yeah, now we're plugging in for I. So now it says at what, we'll call this Roman numeral 2 with serifs, right? At what depth is the intensity 5 lumens? Well, I can either solve for X as a function of I. Let's write that down. This would be part A. If I solve this equation as a function of X in terms of I. Now this looks weird to you, right? Because normally X is our independent variable, but it could be your dependent variable. If you have different intensities, right? Like, I wonder how deep the intensity is going to be 3. I wonder how deep the intensity is going to be 4. How deep will the intensity be 5? So on and so forth. You don't want to have to do the math over and over again. So you would actually solve for X and make intensity your input. And then you could just say, okay, X of 5 equals. So again, that would be beneficial if we had multiple intensity values that we wanted to plug in. But if we're just doing it one time, we don't need to do that. It's easier to plug in and then solve because it's easier to manipulate numbers than it is variables. Unfortunately, though, I still have to somehow communicate that I'm plugging in a 5 for I. And if I can't do it with function notation, how can I do it? Sans function notation. You could say when I equals 5, and then what do we put? Colon, semicolon. Colon, right. Colon. And now we can plug in. Watch, we get log of 5/12 equals negative 0.00235 x, right? And now all we got to do is solve for x. So when we do that, we divide. We get log of 5/12 all divided by negative 0.00235. All right, so notice I haven't even picked up my calculator yet. I solve for x, it's still an equation, right? I have an equal sign, and now I can plug it in. Now, do I need to use the change of base formula to evaluate log of 5/12? Do I need to change the base formula there? No, because it's base what? 10, and my calculator can handle base 10 or base e. Now you could type it in as the natural log of 5/12 over the natural log of 10, but we don't need to do that. So now that we have it, now we go to the calculator. Only at the end. Here we go. We get alpha y equals, boom, or alpha x real, right? Log, and now alpha y equals again, 5/12. Always try to use the horizontal division bars when you can. And then divided by negative 0.00235. Double check, triple check, make sure it looks like it is on your paper, except it's not purple. And then we put equals, we can work straight down, and then boom, 161.792, rounded or truncated, 3 decimals. And now we're done, right? Now we walk away with a smile on our face. Yes or no? No, we're not done. What's the last little thing we need here on our final numeric answer? Units. And what are the units here? Feet. Good. And you can use common abbreviations, right? FT, you don't even need the period after it to show it's a decimal. That's stylized. We call that stylized. Okay. So there you go. If I wanted to know, hey, when will the intensity diminish to 5, from 12 to 5? Well, just short of 162 foot deep. All right. There you go. So it was the last question, but man, there was a whole lot to gain from it, wasn't there? Notation, notation, notation. No notation? No points. All right. Okay. Comments, questions? All right, so I'm going to go ahead and walk around now and hand you a piece of paper that will be your group quiz.